Welcome to the Technology Addicts podcast. In this episode, we'll be diving into an article from the latest issue of Focus magazine, exploring the fascinating world of the all-electric society. Welcome to the Technology Addicts podcast. In this episode, we asked our experts to address the 10 most frequently asked questions about digitalization in the all-electric society. 1. What role do digital twins play in the all-electric society? What does this mean for sensors? Digital twins offer a virtual representation of physical assets, systems, and processes. They enable enhanced monitoring, optimization, and control. These digital twins perform various tasks in the electrified society. Energy flows can be dynamically adapted on the basis of the digital image, for example, by intelligently controlling generators, storage systems, and consumers. Digital twins can also facilitate scenario analysis such as load shifting, grid overload, or energy flows in advance. By continuously mirroring the actual status, maintenance requirements can be identified at an early stage and unplanned outages can be avoided. A digital twin requires sensors that are seamlessly integrated into IT and OT systems and provide data in real time when communicating with digital platforms. Creating a precise digital image necessitates monitoring numerous measurement points, from energy flows to environmental influences and system statuses. 2. What does the increasing integration of renewable energies into the power supply mean for sensors? The integration of IoT technologies and artificial intelligence has led to the creation of an adaptive energy system that relies on precise sensor data. For example, sensors in solar and wind farms optimize operation and enable predictive maintenance by measuring parameters such as irradiation, wind speed, temperature, or vibration. These sensors must be rugged, weatherproof, and low maintenance to ensure accurate measurements over the long term. The enormous amount of data generated also requires sensors with integrated computing power, so-called edge computing, to analyze information locally and respond quickly to critical events. Increasingly, sensors will also need to deliver real-time data to ensure grid stability in the face of fluctuating feed-in. 3. What role do sensor fusion technologies play in energy management? Sensor fusion is a key component in modern energy management. The intelligent combination of different sensor data, for example, temperature, power flow, grid frequency, or environmental influences, provides a more accurate, reliable, and comprehensive understanding of the energy system. This, in turn, enables real-time optimization and precise control of generators, storage systems, and consumers. Additionally, it facilitates condition monitoring and fault detection for predictive maintenance. Consequently, sensor fusion is instrumental in establishing efficient, resilient, and automated energy systems, which are pivotal for the success of the all-electric society. 4. How can the integration of millions of sensors for monitoring and managing energy supply networks be managed and scaled? This necessitates a variety of technological and organizational approaches. Adopting a layered architecture is essential. Processing data directly at the sensor with edge computing reduces data volumes, minimizes latency, and relieves the burden on central systems. Modular, scalable cloud platforms are essential for the central management of sensor networks. Automated commissioning and remote maintenance tools simplify scaling. New sensors can be integrated, configured, and monitored via standardized interfaces, APIs. Standardized, open, and interoperable communication protocols, for example, MQTT, OPCUA, and data formats ensure seamless communication between different sensor types and system components, regardless of the manufacturer. This is crucial for scalability and long-term maintainability. Additionally, robust security measures, including device authentication, encrypted data transmission, and secure lifecycle management, must be embedded from the outset to protect the integrity of the network. Leveraging AI and machine learning, both at the edge and in the cloud, enables advanced analytics for predictive maintenance, load forecasting, and dynamic grid optimization. 5. How can interference be avoided when numerous sensors are integrated into the energy supply system or the energy grid of an all-electric society? Dividing the sensor network into logically separate segments allows local faults to be isolated without compromising the overall system. Here, critical sensors, such as those responsible for grid stability, are given priority. Important sensors are designed redundantly, and communication paths and data processing systems are duplicated in order to mitigate failures. Sensors with integrated self-monitoring report deviations and faults at an early stage. Central dashboards show the status of the entire network in real time and enable intervention. Communication protocols such as MQTT, OPCUA, or IEC 61850 are designed for industrial real-time applications, ensure reliable transmission, and can automatically detect and correct errors. Artificial intelligence recognizes patterns and anomalies in large amounts of data and anticipates potential faults. This enables preventive measures such as load shifting or sensor recalibration. 6. How can the communication of sensors in remote energy projects, for example offshore wind farms, be optimized? An effective approach to optimizing sensor communication in remote energy projects is the use of hybrid communication technologies. This involves combining wireless solutions such as LTE/5G and LoRaWAN with high-capacity fiber optic cables for stable, high-speed connections to the mainland. Meanwhile, satellite communication serves as a reliable backup in particularly remote or challenging locations. Edge computing is also essential for enhancing network performance, as it enables local data processing, reduces the volume of data that needs to be transmitted, conserves energy, and helps prevent network congestion. Establishing a hierarchical structure with data collection nodes further improves efficiency and reliability. In this setup, sensors communicate first with local gateways that act as aggregation points. These gateways bundle and process the data before transmitting it to central systems, resulting in more efficient and stable communication compared to numerous individual sensor connections. 7. How can sensor systems in renewable energy plants be operated autonomously? First, sensors should be energy self-sufficient, utilizing techniques such as small solar modules, vibration energy harvesting, or thermoelectric generators. These energy sources, coupled with energy storage devices like batteries or supercapacitors, ensure continuous operation even at night or in adverse conditions. Second, ultra-low power design is crucial. This includes employing low-power microcontrollers and energy-efficient sensor chips, as well as implementing adaptive measurement intervals and sleep modes to minimize energy consumption. Third, edge computing capabilities within the sensor or gateway are essential. Edge computing reduces communication requirements, conserves energy, and enables rapid responses, such as in the event of faults. It also facilitates first-level data fusion and compression before transmission. Fourth, autonomous sensor systems should incorporate self-monitoring capabilities. This includes monitoring battery status, sensor performance, and communication integrity, as well as performing calibration control and error detection. The system should also be designed to restart automatically in the event of faults. Finally, the physical design of the sensor system is critical. Housings and components must be weatherproof, vibration-proof, temperature-resistant, and low maintenance to ensure long-term reliability in harsh environments. 8. What role does edge computing play in the all-electric society? Edge computing not only reduces latency, but also significantly decreases the volume of data that need to be transmitted, which is especially important when managing millions of interconnected devices. It also allows for rapid response to network fluctuations, disruptions, or load changes, thereby enhancing the resilience and stability of the entire energy system. Additionally, it supports the integration of AI algorithms for fault detection, condition monitoring, and on-site optimization. Edge computing is particularly vital in remote or critical infrastructures to ensure autonomous, low-maintenance, and secure operating processes. 9. Do sensors have to meet special criteria for applications in energy supply networks and in the all-electric society? Due to the stringent requirements for reliability, real-time performance, and interoperability, standard solutions are often insufficient for energy supply networks and the all-electric society. Sensors must operate with high precision and guarantee long-term stability even under extreme conditions such as heat, cold, humidity, vibration. Low maintenance or maintenance-free operation is essential, especially for sensors installed in remote or hard-to-access locations. In power grids, every millisecond counts. Sensors must therefore deliver measured values quickly and with minimal latency, especially for grid protection or control applications. Detecting even small deviations is vital for efficient energy management, making precise calibration and high measurement resolution necessary. Seamless integration into diverse systems is also required, with support for standardized communication protocols such as OPCUA, Modbus MQTT, or IEC 61850. Given their direct connection to critical infrastructure, sensors must incorporate robust security features, including tamper protection, encrypted communication, and authentication mechanisms. 10. What are the most important self-diagnostic technologies for sensors in energy networks? When it comes to self-diagnostic technologies for sensors in energy networks, several methods play a key role in ensuring reliability and accuracy. One important technique is the plausibility check, also known as signal validation. In this approach, sensors compare their measured values with internal reference models or with physical limit values. Using statistical methods, artificial intelligence, or machine learning, they can recognize unusual patterns and identify potential errors. Another crucial method is redundancy and cross-validation. Here, multiple sensors or redundant measurement channels are used to cross-check data. If discrepancies occur between these channels, the system can detect possible sensor faults or failures early on. Many sensors are also equipped with built-in self-tests, often referred to as BIST. These are automated hardware and software routines that regularly verify the functionality of key components, such as processing units, memory integrity, signal paths, communication connections, or analog to digital conversion. Communication and signal diagnostics take this a step further by monitoring the quality and integrity of data transmission. They track factors like error rates, packet loss, and latency to maintain stable connectivity within the network. Drift and aging compensation helps ensure long-term accuracy. Sensors continuously monitor their outputs for signs of drift, offset, or calibration loss. Algorithms then compare current readings to expected baselines and automatically trigger recalibration or send alerts if deviations are detected. Another valuable method is sensor fusion for cross-verification. By comparing data from neighboring or related sensors, such as current and voltage measurements, systems can spot inconsistencies. If one sensor behaves abnormally, the so-called quorum method helps identify which one is faulty. Health and status reporting further strengthens reliability. Sensors keep track of their own operational conditions, including supply voltage, temperature, battery level, and communication quality. When abnormalities appear, they can indicate potential failures before they occur. Modern sensors also increasingly support self-calibration. These devices automatically recalibrate themselves using internal references or by comparing their readings to known external standards, maintaining precision over long periods of time. Finally, tamper and security monitoring has become essential. Sensors can now detect unauthorized access, physical tampering, or even cyber attacks. In such cases, they trigger automatic alerts and initiate protective actions to keep systems secure. Thank you for tuning in to this episode of the Technology Addicts podcast. For more exciting episodes, be sure to follow us on your favorite podcast platform and make sure to check out the show notes.